right, I have 10:30, so let's go ahead and get started. Thanks everybody for coming to my talk today. My name is Jesse Clayton. I'm the Senior Manager of Product for Intelligent Machines at NVIDIA. And what I'm going to talk to you about today is what we're referring to as the AI computing revolution. Now, the original title of this talk was DIY Intelligence, but the more we thought about it, the more we realized we should probably expand the scope of it a little bit. So we will be covering the DIY intelligence part, but we wanted to put it in a broader context to illustrate some of the broader industry trends that are happening right now. I think we'll probably have quite a bit of time at the end of the talk for questions, so if we want to save questions until the end. So first I wanted to get started with a video.
Tires behind the line. 3, 2, 1, charge!
The Space Cookies make their way back into scoring position.
3:30 to beat spot. Able to put a home rubber in. That second shot.
It is a robotics competition, but it really is more than that, in that you're not only doing the robot, but you're branding your team, learning leadership skills.
Is all about inspiring students and others to pursue STEM,
Which is science, technology, engineering, and mathematics.
First Robotics to me is an experience where I can practice all of the things that I've learned in my math and science classes hands-on. It's really amazing to be able to use skills that I've learned in classes and in hands-on applications and be able to see my work come to life and compete at competitions.
Give it up for your Wyoming, Michigan Demons.
I get to learn about engineering. I get to be involved in a really cool program. I get to make friends. I get to learn skills that I can use in industry and in college and in a future job.
Communication skills, public speaking, working with others.
We do a lot of outreach with younger kids, especially younger girls, to maintain their enthusiasm in STEM as they go through school and beyond.
Fantastic coordination as the Cookies now make their way towards the defenses.
This year we have to shoot a lot of really tiny wiffle balls into a goal that's actually mounted horizontally instead of vertically.
And without vision, we won't be able to get the proper angle for that.
NVIDIA recently gave us a sponsorship as well as Jetson TX1, which we're going to be using for the first time on a robot to do some high-level vision processing.
The first 15 seconds of the match are purely autonomous. Our programming is really important during that period of time.
Looks like the Citrus Circus are taking some shots at that high efficiency boiler. 36 kPa in autonomous.
A really key portion of that was our vision.
The Jetson board is actually located on the bottom of our robot, right here. It's notoriously difficult to get a human to accurately align to some sort of target. And so what the Jetson does is it takes a camera through USB and then calculates the angle and distance from a target and then get the robot to drive to a desired position and then shoot.
NVIDIA has helped our team by running a workshop this summer, so many of our members went to learn how to use the Jetson board.
This little camera board right here.
Being able to control things based on how they see the field through the camera would be really helpful for not only getting us a lot more points in terms of accuracy and precision, but also in teaching our programmers how to do more corporate level thinking in terms of programming.
1678, another shot.
I'm hoping that on the programming side, our programming team will get bigger, and not only has NVIDIA helped with that, but I bet they will in the future with more new technology.
Their vision system has helped our robot become even more advanced, so when our robot makes goal after goal after goal because of the NVIDIA stuff, that's a really cool thing.
With 60 seconds remaining, it's anyone's match.
It's really a year-round activity where we get to show other people about STEM and how amazing it can be to participate in science activities.
It's about teamwork and being able to achieve greatness.
It inspires kids to go out in the world and to change it.
That was a video that our marketing team put together to help illustrate some of the work that we're doing with FIRST. This is my 4th year at Championships. Let me Try another microphone. Check, check, check. See if this works any better. This is my 4th year at Championships, and from the very first year I was really inspired by everything that I've seen at first. Every year NVIDIA has increased its presence and its what it's contributed to FIRST. This year, in fact, we sponsored 50 teams worldwide. Now, one of the responsibilities that I think we have in industry is to communicate and provide input back to you who are going to be coming to industry soon about what's happening with broader industry trends, what are the big innovations that are really changing the way that industry works to help you plan your education as well as your career once you get out of college. So guys, we're really at the beginning of a new era in computing. And we say it's a new era because it has all the indications of things that have marked new eras in computing. They're all defined by fundamental shifts in the way that computing is done, whether it's programming or the way that users use computers. One of the most recent eras started with the PC and internet revolution. So this, of course, was driven by companies like Microsoft and Intel and Yahoo, and it really opened up computing and opened up the internet to 1 billion users worldwide. In the last decade, we had the mobile cloud revolution. This was driven by the iPhone, Amazon Web Services, and now opened up computing and computing resources to users worldwide. Over 2.5 billion people now had access to technology that they didn't previously have access to. And we're just at the beginning now of the AI and IoT computing revolution. In the future, there will be hundreds of billions of devices powered by artificial intelligence, serving many different purposes and solving many different problems. Now, many people know NVIDIA as a company that does computer graphics, and that's true. That's where we got our start. But we recognized early on that the GPU, which is our invention, can be used for many general purpose computing tasks as well. So that realization has allowed us to provide solutions into things as diverse as professional visualization, supercomputing, and now intelligent machines. GPUs are used to simulate virtual worlds, and you can think about this like computing human imagination. GPUs are used to power artificial intelligence. You can think about this like computing human reason. And so that's really what NVIDIA is about, is amplifying imagination and intelligence. So taking a step back, what's really the significance of a GPU? Well, very simply put, a GPU is a parallel processor. So in your computer, in your robots, you have CPUs that have maybe 1 to 8 cores. They're very complex cores. They have a lot of features like speculative branching, out-of-order execution, and they're very good at executing serial tasks very quickly. So managing your file system, taking input from users, managing the operating system, those tend to be very serial tasks, and CPUs have been optimized for those use cases over many, many years. Now, a GPU is different. It has many hundreds or thousands of simple cores. They don't have the level of complexity that you would find in a CPU, but they can do simple things like add and multiply, and since there's so many of them, they can do these things in parallel. Now, there's some problems that turn out to be very well suited to parallel processing. Some problems are serial problems, some problems are parallel problems. For those parallel problems, GPUs make a lot of sense. Now, GPUs were originally developed for graphics. That's where the G comes from in GPU, graphical processing unit. And rather than tell you why that tends to be a parallel problem, I want to play another video that illustrates it.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it,
So
as
I'm
a
going to pause
series
this
of
for a
discrete
second and see
actions
if we can
performed
get the sound
sequentially,
fixed.
one after
do we have any AV? Is there anything we can do? Okay. Unplug my, so it's going through VGA. Does my mic sound okay when I'm talking? Okay. Yeah, it's not playing out of the speakers. Okay, we'll just try the other way.
Leonardo.
There are not in some of these.
All right, I introduce to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed.
So this is a video that we worked with the Mythbusters guys a few years ago to put together to help illustrate the difference between CPU processing and GPU processing. So they built these paintball robots to illustrate the difference. This is the CPU version. This is supposed to be a painting, of course, of a face.
Leonardo 2.0.
This is the GPU version.
Trigger on this thing. 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully. When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10, 9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So as you can imagine, rendering graphics to a display, you're rendering each pixel individually. Well, it's so much better if you can render those pixels in parallel rather than rendering them one at a time. So that's where the GPU comes from. So like I said, the GPU got started in computer graphics. Back in the 90s, it was a very fixed function processor. It did a small number of things. It did them very well. And at the time, this was when I was just exiting high school, these were very compelling computer graphics. Now by 2003, companies like NVIDIA introduced programmable shaders. And for the first time, developers could start thinking about the GPU as a more flexible platform that they could use for more general purpose computing. Of course, this created many new opportunities in computer graphics, but it also opened the door to other kinds of research. That was the springboard from which researchers developed GPU techniques for general purpose GPU computing. So now researchers could use a GPU for tasks that were general purpose. They could program the GPU using C, which is a very familiar development platform for a lot of developers. So that first happened in 2008. That's where NVIDIA launched its first general purpose GPU computing platform called CUDA. And of course, researchers and developers have continued to innovate on top third thing is GPUs. These new algorithms are parallel in nature, and they require a general purpose parallelized architecture in order to run efficiently. So these three things, big data, algorithms, and GPUs came together in 2012 in a landmark piece of research in which researchers had really crashed the state of the art for image classification. There's a challenge known as the ImageNet challenge. The challenge is that you have to develop a system that you will train on a data set, and then it learns how to classify images in a new data set. So for instance, there's lots of cars in the data set, lots of dogs in the data set, lots of instruments in the data set. And through that process, it learns how to detect the different things in these images. So in 2012, researchers applied deep learning to this problem. And in 1 year, they were able to reduce error rates by 40%, going from an error rate of 26% down to 16% for image classification. That means that 16% of the time it got the wrong answer when it was trying to understand what was in the image. Now the research continued to advance after that. In fact, in 2015, both Microsoft and Google announced deep learning-based approaches in which they had performed better than humans. That means that their systems were able to classify images more accurately than humans can. Since then, work in deep learning has branched out into many other fields, and deep learning is proving to be a very capable technique to solve a lot of thorny problems in artificial intelligence. In many cases, it performs better than all previous solutions, and in some cases, it performs better than humans. And so for that reason, the next step in the evolution of the GPU is around AI computing. Now, just in the last year, there have been some really tremendous results achieved with AI computing. Researchers have taught AI to play the game of Go. This is a game that's so complex it has more possible boards than there are atoms in the known universe. And they not only taught it how to play the game of Go, but it beat a reigning Go champion. So back several years ago, when IBM had developed, I believe it was Deep Blue to play chess, it was heralded as a great achievement that it had beat the chess champion at the time, Garry Kasparov. At the same time, researchers said, this will never happen for Go. Go is too complex of a game. Well, deep learning, because of its neural network-based approach, is able to understand the game at a more intuitive level and come up with strategies to beat Go champions. Researchers taught an AI to play the game of Doom, which is not just about pointing and shooting, but also path planning and navigation in complex mazes. Researchers taught AIs to learn how to paint in the styles of the masters, to synthesize voice to make text-to-speech much more natural and conversational, to caption photographs, so to not only understand what's in a photograph, but what's important in that photograph, how those different things relate to one another. To learn motor skills. This is a complex activity that takes humans months to develop. To learn how to walk, which is basically motor skills with the added constraint that if you don't do something fast enough or at the right time, you fall over. And of course, to learn how to drive a car. Self-driving cars is research that NVIDIA is very heavily involved in right now. Because of what's been shown to be possible with deep learning and AI, the computing ecosystem around AI is developing very quickly. There's a race right now happening among mobile consumer service providers to develop new products and services inference is still challenging, but it's not nearly as computationally intensive as training. And so inference can be deployed to small devices on small platforms for use in drones, for use in smart cities applications, for use in robots, for use in cars, etc. So let me go into some examples of how this process actually looks on the inference side. Usually we show this as a live demo. I have the ability to set that up. Is there any way we can turn off the lights so we can better see this? I think it'll be hard to.
This could be it. Hopefully it's not far. Yeah, it's not.
No?
I don't know where the lights are.
Okay. So if you want to come up after and get a better look at this, I can show it to you, but I'll try to describe with the lighting conditions what's happening here. So this is a tool called the Deep Visualization Toolbox, and this is really available for anybody to download and install on your Linux system. But it's a really good tool for understanding how neural networks actually work. So we trained a neural network on over 1 million images in the ImageNet data set, and now that network is able to do inference. We can show it new images it hasn't seen before, and it'll tell us what is in those images. So here, it's never seen this picture of this ambulance before, but it's telling us with 95% confidence that this is, in fact, an ambulance. And it could do this for cheetahs, jaguars. So this one's kind of interesting. It says with 73% confidence it's a jaguar. With 7% confidence it thinks it's a leopard. So you can see how it kind of get those. Those are pretty close animals. In fact, I'm not sure that I can tell the difference. Now this one's interesting because this is obviously not a real picture. It's been photoshopped. But if you were to ask me what it was, I might say it's glass or it's a bubble. And it's interesting that the neural network can come up with a human-like interpretation of what this could possibly be, even though it's not a real thing. So it's saying with 16% confidence this is a bubble, 6% confidence that it's sunglasses. Okay, so what's actually happening in this neural network? Well, the way a deep neural network is structured is by layer. At the first layer is where you're feeding the data in. Since we're working with image data, we're feeding in the pixels to this first layer. And this first layer is looking at small regions of the image, so say 11 by 11 or 9 by 9 pixel regions of the image across the entire image. Now these here are all the neurons in that layer, and each of these neurons is detecting a different type of feature about those 11 by 11 pixel images. So this neuron right here, we can see, is looking for vertically oriented edges. So a light area next to a dark area. And you can see on the ambulance all the places that are exciting this neuron. So all these 11 by 11 pixel regions that are exciting this neuron. So this vertical corner panel here, light corner panel with the dark window, the light back with the dark tail light right next to it. And each of these neurons is looking for something different. So if we look at the neuron next to it, this one's looking for the opposite. So vertically oriented edges, instead of going dark to light, going light to dark. This one's looking for horizontally oriented edges. And it turns out that for image classification, this is what comes out of the training activity. Nobody told the neural network that you should look for edges. It just learned through the process of being exposed to many, many images, guessing at what they were, being told, no, that's not right, go back and retrain until you get the right answer. It learned that edges are a good way to distinguish between ambulances and jaguars and other things. Now, as we get deeper into the neural network, into subsequent layers, it's looking for aggregations of previous layers. So instead of looking for 11 by 11 pixel areas and thinking about them as pixels, it's looking for collections of 11 by 11 pixel areas, and you start to see some structure emerging from the thing it's detecting. So this neuron here is looking for a red region next to a sort of last layer, and it's putting them all together to recognize an ambulance. Now these are some of the ambulances that were in the training data set. And it's interesting, all these ambulances, the photograph is from the front. In this image here, which it hasn't seen before, the photograph is from the back. And so the neural network has figured out how to generalize what an ambulance is. It doesn't have to be an ambulance from the front only. It's learned that ambulances consist of these collections of features that it's learned through the training process. So if I were to speculate, I would say ambulances have a red region and a white region, and they tend to be alternating stripes going sideways. There's some lettering on the side, there's some wheels, et cetera, et cetera. But again, the neural network has figured out these are the things that make an ambulance. Now, all these other boxes here are other possible candidates. Again, these are the neurons in the layer at the very end of the network. Each of these neurons corresponds to candidate classes that it could have picked. So let's look at some other ones. So the ones that are light are ones that are saying it's high confidence that it could be one of those. The ones that are dark is saying it's low confidence. So here's another one that's relatively light. So you can see how it got there. These are delivery trucks. And it's saying with somewhat confidence, not as high as what it actually selected, somewhat confidence, this could possibly be a delivery truck. Well, delivery trucks are kind of like ambulances. They have wheels, they have sides, they kind of look like things that would drive. So let's look at another one that the neural network says it's no way it's one of these. Let's look at one of the very dark neurons. So it says there's no way this is a French horn. Very low confidence that this could possibly be a French horn. And if you think about this from a human perspective, that kind of makes sense, right? French horns have very different visual characteristics than ambulances. Okay. Now, this is a very simple demonstration of how deep learning works. Of course, after applying it, there are many other things that you can do. And I mentioned before that NVIDIA is very involved in self-driving cars. So I want to share another video with you on some of the work that we've done to apply this technique to self-driving cars.
Oh yeah, good. The universal sign is also
What happens before you train?
so cool.
examples are actually, as you can imagine, very thorny problems because we have so many unconscious rules that we ourselves use to drive in construction zones, because construction zones don't have very good rules, and yet we manage to get through it safely, that there's really no good way to come up with a programmatic way to tell a computer how to do this. So if you simply expose a neural network to this situation many, many times and tell it what the right answer is by example, it has this ability to generalize to many different situations. And so you can drive it through several construction zones, and it will learn to generalize to a new construction zone that it hasn't seen before and navigate correctly. Okay, so let's bring this all back to DIY intelligence. How do we as developers take advantage of this capability to solve some of the problems that we care about? So NVIDIA just launched a product called the Jetson TX2. And I'm not going to spend a lot of time on this because this is really just illustrative. The previous generation, Jetson TX1, the developer kit was available as part of First Choice this year, and many teams have successfully used it in their robots for computer vision and for other tasks. Jetson TX2 is the next generation, so we'll have more performance, more capabilities for artificial intelligence. So we call this artificial intelligence at the edge. That's to differentiate from artificial intelligence in the data center. If you're using Siri, Siri is reaching out to the data center to make inferences on your voice data. If you're using Pinterest image search, Pinterest is reaching out to the data center to make inferences on your image data. But if you're a robot, if you have a robot, you don't have a connection back to the data center, or maybe it's not a reliable connection. You need to make decisions quickly where you can't rely on that round trip to go back to the data center. So you need a small, capable processor that's able to do the level of computation needed for artificial intelligence in the size and power envelope that's typical of robots, drones, and other similar applications. And so that's really what Jetson's all about. This is just some specifications of Jetson compared to the previous generation. If you're familiar with Jetson TX1, Jetson TX2 has more performance. The newer generation GPU, twice as much memory, more flash storage, Wi-Fi, more video encode, more video decode performance. I don't want to go through all these. You can find the specs for this on our website. But the real power that allows developers like us to take advantage of the AI capabilities comes from the software stack. And so that's an area that NVIDIA and other companies really focus on. And we think about this in kind of 4 different areas. So the first is deep learning. That's a lot of what I've been talking about today. Accelerators and libraries for deep learning to accelerate deep learning workloads on Jetson and other products. The second is computer vision. Now, I've been differentiating between deep learning and traditional computer vision. There are many problems that have already been practically solved with computer vision, so there's no reason to port those to a deep learning workflow, which is more computationally intensive. NVIDIA provides accelerators for computer vision as well. Computer graphics, you might ask yourself, what does computer graphics have to do with artificial intelligence? Well, many times, almost invariably, these systems at some point have to communicate their result to a human in a way that's easy to process, is understandable, and enables them to take action. So graphics can be tremendously helpful in that, whether you're putting bounding boxes around the thing that it's detecting, or doing some sort of other overlay to provide a human with actionable data. And then, of course, media. Building a system, of course, involves managing media from various types of sensors, and media APIs the glue that really pulls all these pieces together to enable developers to make end-to-end systems that leverage deep learning, computer vision, graphics, and management of media. The developer site is where developers can go who want to take advantage of Jetson on their robots or other applications. And NVIDIA's strategy with Jetson is to make everything publicly available. So all of the software, the libraries, the developer tools, design collateral for the board in case you want to make your own carrier board for it. A developer forum to ask and get answers to questions, training and tutorials to help you learn how to use Jetson for deep learning, for computer vision, for other applications, and then an ecosystem. So this is really good if, for example, you're looking for a carrier board for your Jetson so it can more easily fit onto your robot. Now, there's been a lot of adoption of AI technology in industry of this capability. So the same Jetson that many teams this year are using in their robots is also leveraged by industry to solve many problems in AI. So Cisco uses Jetson for an enterprise collaboration search and rescue drone. This delivers first aid or packages to people who may be lost out in the wilderness, and it uses deep learning to help detect where those people are. Aerotronics uses deep learning for industrial inspections to detect faults in infrastructure like wind turbines and cell towers, so that those can be scheduled for repair. Socialize is using deep learning for ophthalmology. So looking at a retinal scan that you might get when you go to the eye doctor, they send this through their neural network, and it will tell where the potential problems are in that retinal scan. So today it might take a doctor 10 or 15 minutes to do that process, which makes it impractical to bring to third world areas where there just aren't enough doctors to do this. Now they can run it through a deep learning system and get similar results to what you could achieve with a doctor, making it possible for many third world areas to get this kind of health care. And of course, Jetson is being used in academia and research as well. Okay, so resources that you can use to learn more about deep learning are available from NVIDIA. So the first is what's called the Deep Learning Institute. If you want to learn more about the theory behind deep learning, how it works the way that it does, and start to get your hands dirty with it, you can go here. There's training material, hands-on labs that you can use with Amazon Web Services or Microsoft Azure, so you don't even have to buy any hardware to get started. And nano degree programs through Udacity. You can actually get a nano degree in self-driving car development using artificial intelligence through the Deep Learning Institute. Next thing is 2 days to a demo. This is something that we developed around Jetson. This will enable you, if you have 2 days of time to spare in a Jetson developer kit, to generate a deep learning demo using even your own data set. So this isn't even a pre-canned demo. You can actually use it to train your Jetson with some of your own data to exercise deep learning. Inception is the next thing. So as you get into your university studies, if you start to think about what you want to do after university, assuming that's the direction that you want to go, Inception is a program for startups to get access to NVIDIA resources around GPU and artificial intelligence technology. And then, of course, the GPU Technology Conference. This is the largest GPU conference in the world. We have many tracks there that include research, academics, OEMs, and we also have something there we call First Day. So we invite first students to come learn more about some of the things that I talked about today, do hands-on work with Jetson using deep learning and artificial intelligence. The Jetson TX2 developer kit is available today. It's available for $299 for first students. If you go onto our website and enter in your first team information, you'll be able to get that discount. That's everything that I wanted to cover today. How are we doing on time? Okay, so we got 8 minutes left. So I guess now I'll open it up to questions. Certainly. First slide. Yeah. Yes.
What is a neural network actually composed of? What makes it actually like contain the factors that allows you to identify what you want to identify?
Great question. Yeah, so it's really just a directed graph. So you have the data structure for a neural network. You have a series of nodes, which is a layer, and those nodes are connected to the next layer through what we call connections. Now, the way that it actually gets trained is there is different weights between those connections, and there is a function for assigning those weights as you go through the training process. So let's say the first step through a neural network, those weights are just assigned with zeros or with noise or however it's initialized. You show it a picture of a car. It spits out some answer dog, right? It's not a dog. So you tell it to go back and tune the weights until it is able to correctly classify that car as a car. So the first time through, it's pretty straightforward. It's just one thing that it's learned. The second time through, now you show it a picture of a bus. It already has some weights that it's code that you're writing is setting up the network, and you can find code for that available online, and then sending the images through the network, and then basically telling it when to stop. There are a lot of tools available that can help you with that process. NVIDIA makes some software called Digits that you can use for Microsoft Web Services to basically train the network. And so the code is much more high level. It's really more about visualization and processing rather than the down to the details of doing computer vision. Yes?
Can I ask about some, can I ask about the power for the Jetson TX2?
I'm sorry, can you say it louder?
Can I ask you about the power on the Jetson TX2?
Yes.
So say if you were to train like the Safari 10 dataset to 93% accuracy, how long would that take?
So you typically wouldn't do training on the Jetson itself, because training is very computation intensive and very memory intensive, and so it'll be much more efficient to train it on a big GPU like a Titan, or to train it in the cloud with Amazon Web Services or Microsoft Azure. And so training times, depending on the type of network and the data set that you're using, could take anywhere from an hour to a day, or in some cases, some of the really big networks and really big training sets that people are working on may take a week on some of these big GPUs. Yes? Yeah, absolutely. So it's a very, the question was, if you train a neural network enough, can it recognize stylized pictures? And the answer is absolutely yes. Neural networks are a very abstract construct, and so there's no inherent limitation on the things that it can or cannot detect. One way to think about it is, if it's something that a human can come up with a rationalization for, then it's something that a neural network will probably be able to do. Now, what you would do differently in that case is you would train it with stylized data, and it will give you more accuracy for stylized data. Yes?
Can you give us an example of some of the scope beyond just visual data that neural networks can learn about?
Yeah, so the question was, can you give us an example of what beyond visual data can neural networks use? Natural language processing has been a very popular application of neural networks. So basically interpret what I'm saying and take some action based on that. So Siri uses natural language processing, for instance. Medical diagnosis, which is also image data, but it's a little bit different application than what we've been talking about here. Financial modeling, so understanding based on economic signals what is likely to happen for a financial institution or an industry. Insurance rate adjusting. What are some other ones? I mean, there's really all kinds of different data. Oh, anomaly detection. So let's say you have a big factory and you notice that this motor is starting to behave a little bit differently. And as a human, you don't know what that means, but the neural network may have learned that, oh, that means that this machine's going to break in 3 months. You better get it scheduled now so it doesn't leave you entire factory running. Yes?
So, how would, I know it's a little bit different, but like, you know the Microsoft AI that was uploaded, I think, like 2 years ago on Twitter? And then,
yes.
like 4chan, like found it, and then like after a couple hours.
Yes, yeah. Shut it down, yeah.
Well, yeah, how do you, or how would they protect something like that from fake information?
Yeah, so the question was, Microsoft launched a chatbot a couple of years ago, and it very quickly started to spout out a lot of inappropriate responses. And it's basically, how do you protect against something like that? So what they did is they basically opened it up to anybody could chat into it, and from those responses, it itself would learn what were appropriate responses. And there are a lot of people on the internet who like to do inappropriate things, and through that process, it learns inappropriate behavior. And so the ways that you might avoid doing that are maybe you pre-train it on the sorts of things that are inappropriate and tell it not to learn those things, or you simply do your training internally where you can control the sorts of things that it's trained on. Obviously, there's positive and negatives of doing each of those things. Yes?
So when you're using a neural network to approach different kinds of problems, say like image processing versus voice recognition, what kind of changes would you make to the network to make it more efficient and efficient?
Yeah, good question. So if you're doing a different type of solving a different type of problem, how do you determine what kind of a network you use to do that? So the first answer is rely on the have done a lot of work to demonstrate what types of networks tend to be good at these things. But we're really just at the beginning of this, and so the bigger answer is we're still figuring it out. A lot of it is based on intuition. For example, in robotics, people observe that, well, robots need to have sort of an understanding of what's happened just recently, not what I'm doing it right this second. And so they hypothesize that if I put a feedback loop in my neural network, then it will be able to sort of take advantage of that thing that it just noticed a second ago. This is also used in natural language processing. So if you're processing natural language, you need to know not just the word that I'm saying, but the previous few words that I said as well for context, because otherwise the words might not make sense. And so researchers speculate that, if we put a feedback loop in the neural network, that will give it that sort of short-term memory capability. So a lot of it really is kind of intuition and doing experimentation to figure out what's going to work if you're going to forge an area that nobody's kind of waded into yet.
Yes. Is there like the publicly viewed source code for like the example you showed earlier that classified the ambulance anywhere, like on the internet or anywhere?
Yeah, absolutely. So the question is there publicly available source code for that example? So I believe the Deep Visualization Toolkit itself is public. So if you just Google Deep Viz Toolkit, you'll find it. The network is AlexNet, which was a network from back in 2013, I think, for image classification, and that's freely available. And then the training data set is called ImageNet, and that's freely available for download as well. And you can find lots of examples online of how to actually set that up and get it working. Yes?
How do you condense the data from the small little 9 by 11 pixels that you get? Because I'm assuming that you'll get like 1 million of them or whatever with different pictures, and they might be the same little 9 by 11 code. So then how does the system be able to recognize that this one is the same as the one from the other picture and be able to condense it and save space from that?
So I believe what you're asking is, you're giving it all these pictures, how do you prevent the neural network from just being a picture database?
Yes.
Okay, good question. I like to think of neural networks as sort of lazy functions. A neural network can approximate any function, and in this case I'm using the term function very abstractly, like classifying an image as a function. And so through this process of training, it sort of learns what is the laziest way that it can get to this result. I mean, this is very much like humans learn. If you're trying to hit a tennis ball, you're not doing calculus in your head, trying to figure out exactly where to hit that tennis ball, right? You sort of encoded in your brain in a very lazy way that takes the least amount of space how I can hit that tennis ball. And so neural networks kind of do the same thing. Those weights and connections between nodes are the encoding for those pictures. So it doesn't actually encode the pictures themselves. Yes?
So do you think that with deep learning in AI, a robot could effectively learn to play physical sport like soccer or something?
Yeah, good question. So